All right, let's talk about one of the most critical survival mechanisms for any large-scale system out there, load balancing. And look, this isn't just some boring networking trick. No, this is the secret sauce that separates a system that thrives under pressure from one that just, well, completely falls apart.
And right there, that's the paradox we're diving into today. You've definitely felt this before, right? A website crashes during a huge sale or a big game, but the company swears up and down they had more than enough servers to handle the traffic. So what gives? How is that even possible?
Because when you peek behind the curtain, this is what you see. The actual machines, the servers themselves, a lot of them aren't even breaking a sweat. They're just sitting there, completely idle, waiting for something to do. The system as a whole has all the raw power it needs. CPU, memory, you name it, it's all there, ready and waiting. So the problem isn't a lack of capacity. The problem is how that capacity is being used, or, not being used. This is the million-dollar question. If you have all the power, all the resources, why does a sudden, lopsided flood of traffic bring the whole thing crashing down? Well, the answer is all about the art and science of distribution.
So, here's how we're going to break it all down. We'll kick things off with that capacity paradox, then we'll really get into what a load balancer's real job is. From there, we'll cover the simple strategies, move on to the smarter, more dynamic ones, and even see what happens when the balancer itself breaks. And we'll wrap it all up with the absolute core truth about system survival.
All right, first up, the capacity paradox. It's this wild idea that just throwing more hardware at a problem isn't always going to fix it. Okay, section 2, let's really dig into what's going on here. It is so much more than a simple networking trick.
And this is where it gets really interesting. On the surface, yeah, a load balancer just spreads requests across a bunch of servers. Simple enough. But if you zoom out to the systems level, what's really happening is dynamic resource allocation under uncertainty. It's making critical decisions in real time with incomplete and often messy information.
See, a load balancer isn't just a static, set it and forget it kind of thing. It's a nonstop decision-making engine. For every single request that comes in, it's asking, who gets this? Which server is already swamped? Which one looks like it's about to fail? Who should we just plain avoid right now? It's basically the brain of the entire operation. Okay, so how does it actually make all those decisions? Let's start with the basics, the foundational tools that every engineer learns to tackle this problem of lopsided traffic. Here we have the 3 classics. First, you've got round robin. It's the simplest. Just go down the list one by one. Server A, then B, then C. It's fair, but it's kind of dumb. It has no idea if a server is struggling. Then there's random selection, which is exactly what it sounds like, and it works surprisingly well. And finally, least connections, which is a bit smarter. It sends new work to the server that's doing the least amount of work right now. And this is one of those ideas that just feels wrong at first, but is absolutely crucial. Sometimes just picking a server at random is way better than a rigid, fair system like round robin. Why? Because you avoid creating these weird, accidental bottlenecks. Turns out complex systems actually love a little bit of chaos. But, those simple strategies will only get you so far. To build systems that are truly stable and can adapt to anything, you need to pull out the bigger, smarter tools. And that brings us to consistent hashing. This is a brilliant algorithm used in pretty much everything from massive databases to content caches. Now, its main goal isn't perfect even balancing. No, its main goal is stability. When a server suddenly joins the group, or worse, disappears, consistent hashing makes sure that the disruption is as small as possible. The best way to think about it is with this ring. Imagine you place all your servers at different points on the circle. Then you place a user's request on the circle too. The request just gets handled by the first server it finds as it moves clockwise. Simple, right? But the real magic is what happens when a server is removed. Only the requests assigned to that server have to move. Everybody else stays exactly where they were. It's an incredibly elegant and stable solution. Now, modern load balancers take this to a whole other level. They're basically sophisticated feedback loops. They are constantly observing the system's vitals, latency, error rates, how busy the CPUs are. Based on all that data, they decide to adjust things, maybe giving a struggling server a little less traffic for a while, and then they correct the flow of traffic in real time. It's just this constant loop. Observe, decide, correct. But here's the twist. The very tool that's designed to stop your system from failing can, sometimes, become the thing that causes the failure. So what happens when the load balancer itself gets it wrong? Well, it can lead to some truly catastrophic failures.
You can get a hotspot, where one poor server gets absolutely hammered while its neighbors are doing nothing. Even worse is a cascading failure, where that one overwhelmed server dies, and its load shifts to the next one, which then dies, and so on, like dominoes. Then you've got thundering herds and retry storms, where all the users try to reconnect at once, basically DDoSing your own system.
And this leads us to one of the hardest but most important lessons in system design. A truly smart load balancer knows when to just give up. It is so much better to turn away a few users by dropping the requests than it is to accept everyone and risk bringing the entire system down for everybody. It's all about survival. So let's bring this all home. We're going to zoom out from the nitty-gritty technical details and talk about the fundamental reason we do any of this stuff in the first place. First, you have to understand this isn't just about websites. Load balancing as a principle is absolutely everywhere. It's happening inside your databases, across global CDNs, in the message queues that power your apps, and even in the cloud schedulers that decide where to run your code. Pretty much every large system you can think of is built on multiple complex layers of load balancing. And here is the first piece of our final big insight. A load balancer can't just magically create more servers or more power out of thin air. What it does is unlock the capacity you already had, but that was hidden by that lopsided, uneven distribution. It reveals the true power of your system, and just as important, it protects that system from destroying itself. And that's the bottom line. The ultimate goal was never about achieving perfectly equal, fair distribution. That's a total myth. The real goal, the only one that actually matters, is keeping the lights on. It's about making sure the system as a whole can continue to serve users, even when it's under attack, when parts are failing, and when the world is completely unpredictable. The goal is survival.